Before a skyscraper could rise or a bridge could be built, men had to descend beneath the riverbed into pressurized darkness, in chambers where the air itself could kill you, not immediately, but on the way back up. Before a single steel column could be raised, someone had to dig down to the rock that would hold it, and in the 1870s, no one yet understood what that work would do to the men who did it. How do you build foundations beneath a river? By the 1870s, New York was under pressure of a different kind. New buildings were growing heavier. The ground beneath Manhattan, much of its soft clay, sand, and glacial fill, could not hold them. Engineers understood that the only reliable foundation was bedrock. In Manhattan, that bedrock could lie anywhere from near the surface to more than 100 feet below grade. To reach it beneath open water, engineers turned to a technology borrowed from European bridge construction, the pneumatic caisson, a massive timber box sealed at the top and open at the bottom, lowered onto the riverbed. Compressed air pumped inside kept the water out. Workers entered through airlocks, and at the bottom, in the pressurized dark, they dug. The engineering logic was sound. What no one fully understood yet was what sustained exposure to compressed air and rapid return to normal pressure would do to the human body. In 1870, Washington Roebling was 32 years old and the chief engineer of the Brooklyn Bridge. His task was to sink 2 pneumatic caissons to bedrock beneath the East River, one on the Brooklyn side, one on the Manhattan side. Each caisson measured roughly 170 by 100 feet, larger than anything previously attempted in the United States. Over the course of the project, 600 workers would labor inside them. Roebling did not oversee from a distance. He descended into the caissons himself to inspect conditions and maintain the confidence of his men. A worker entering the caisson passed through a small iron airlock, a cylinder barely wide enough to stand in. The door behind him sealed. Compressed air hissed in. His ears popped. The pressure equalized. The inner door opened. Inside, the working chamber was perhaps 8 feet high. The ceiling was the underside of the timber box above, lit by candles and early gas lamps. The floor was the riverbed itself, mud, gravel, boulders, and whatever the East River had deposited over centuries. The temperature hovered around 80 degrees Fahrenheit, even in winter. Workers stripped to the waist. They dug with shovels, picks, and, when they hit stone, dynamite. The excavated material was forced up through pressurized tubes to a dredging bucket above. As the material was removed, the caisson sank. Slowly, day by day, it descended toward bedrock. The deeper the caisson sank, the higher the pressure required to keep the water out. At the Brooklyn Tower, workers reached a final depth of 44 feet below the river surface. On the Manhattan side, the caisson descended to 78 feet, 6 inches, still short of bedrock. The pressure inside reached levels equivalent to working more than 30 feet underwater. Workers spent shifts of several hours in these conditions. When their time was done, they returned to normal atmospheric pressure, often within minutes. And then, sometimes hours later, it began. Joint pain, paralysis in the legs, stabbing abdominal cramps, slurred speech. Some men could not stand. Some collapsed in the street on the way home. On April 22, 1872, a German laborer named John Myers became the first worker to die from the condition, suffering abdominal pain and collapsing at home after only his second day on the riverbed. The workers called it the bends, because the pain forced them to double over in a posture that resembled a fashionable stance of the era known as the Grecian bend. The engineers called it caisson disease. No one yet understood what caused it. In 1872, Washington Roebling spent 12 consecutive hours in the Manhattan caisson. He rose to the surface. He collapsed. He was carried home. His lungs were congested. His legs were partly paralyzed. He had symptoms that would never fully leave him: sensitivity to light and sound, deteriorating eyesight, chronic pain. He never returned to the construction site. For the next 11 years, he supervised construction of the Brooklyn Bridge from his bedroom window in Brooklyn Heights, watching through a telescope, dictating instructions to his wife Emily, who carried them to the site. The bridge he was building rose outside his window. Washington Roebling's physician on the project was Dr. Andrew H. Smith, a throat specialist with no prior experience of compressed air illness. He was the first to formally name what he was seeing. In 1873, Smith presented 110 documented cases of caisson disease to the College of Physicians and Surgeons in New York. Symptoms included joint pain, paralysis, and vomiting. 3 had ended in death. He published his findings that same year, the first systematic medical description of what we now call decompression sickness. Smith understood that rapid pressure change was the key factor, but not yet why. The cause, nitrogen bubbles forming in the bloodstream during too fast decompression, would not be established until French physiologist Paul Bert published his foundational work in 1878. Smith's practical interventions still mattered. Shorter shifts, better ventilation, exclusion of unfit workers. His actions reduced the rate of serious cases, though they could not eliminate it. For the men working in the caissons, the danger was invisible and poorly understood until it had already struck. There was no decompression protocol, no recompression treatment, no way to predict who would be affected. When Roebling finally halted excavation on the Manhattan side at 78 feet, well short of bedrock, it was not an engineering compromise. It was a calculation. To reach bedrock, he estimated, might require 100 more deaths. He stopped and placed the Manhattan Tower on compacted sand instead. The tower has not moved in over 150 years. The men who worked the caissons were called sandhogs, a term that would persist for generations of underground construction workers in New York. Their knowledge was entirely experiential. There were no training programs for compressed air work, no established safety procedures at the start of construction. What existed was the accumulated observation of men who had survived, which postures reduced the pain on decompression, how long a shift could safely last at a given depth, which symptoms could be walked off and which demanded immediate attention. The Brooklyn Bridge caissons were completed in 1872 and 1873. The bridge itself finally opened in May 1883. The pneumatic caisson technique did not end there. Through the 1880s and 1890s, as Manhattan's skyscrapers grew heavier, caisson foundations moved from bridge piers to the columns of office buildings and skyscrapers. By 1908, the Manhattan Municipal Building used caissons sunk 144 feet below grade, deeper than anything attempted on the Brooklyn Bridge, with workers now operating in scheduled shifts with dedicated medical monitoring on site. The practice had been refined enough to become standard, the invisible infrastructure beneath buildings that would define the 20th century city. These systems shaped the world quietly. If you'd like to see more of them preserved, consider subscribing. And tell us, which forgotten craft should we document next?